Hello friends, welcome back to You Can Do TV. Ask most people who built their car and they'll name a brand, but that brand didn't cast the hub, forge the bolt, or braid the hydraulic hose rated at 6,500 psi. Behind every finished vehicle sits a hidden layer of foundries, heat treatment plants, bearing specialists, and gear shops exporting across 5 continents. Watch to the end for the part nobody buying a car ever realizes. You think a car is born on an assembly line? It isn't. Long before the body ever drops onto the chassis, thousands of small steel pieces have already been shaped, hardened, and measured. The rotor shaft is one of them. In an electric powertrain, it spins at speeds up to 20,000 RPM, more than 3 times faster than a Formula One engine at redline. Why does that matter? Because the tiniest imbalance at that speed turns the shaft into a very expensive vibrating rod. It starts as a plain steel tube, heated red-hot at one end, then reshaped inside a die. And yet the small parts get the same treatment. Every step happens without releasing the workpiece. Press fit, induction preheat, laser weld, 10 seconds per cycle. Some of the smallest components are trusted with the biggest loads on the entire vehicle. Turns out they do, and it starts with a lump of metal you have never once looked at. The wheel hub, load, rotation, and braking force all meet inside it. Cast, machined, checked to 1/100th of a millimeter. Now, the disc that stops your car when it matters most starts life as a stream of glowing orange liquid. Brake discs get cast, machined, and finished in factories large enough to power themselves off their own solar roofs. Molten iron pours in one end. Finished discs come out the other. Move from passenger cars to trucks and buses, and the scale changes completely. 15 million wheel hub assemblies, shipped 5,800 people employed. All from a component nobody on the road will ever point at. A loaded truck weighs 40 tons, and every one of those tons rides on the wheel hub, the piece that holds the wheel, the bearings, and the brake disc together as one rotating unit. Inside that hub, the bearings are what stop everything from welding itself together through pure friction heat. You do not want to be the driver who finds out what happens when a hub assembly lets go. Every bolt is cold forged, thread rolled, plated, then tensile tested until failure. Those bolts hold the car together, but an electric car actually moves because of a component few people ever see, spinning fast enough to destroy itself if made wrong. A rotor shaft begins as nothing more than a plain steel tube before heat, pressure, and machining reshape it completely. Tubes between 25 and 90 millimeters in diameter. Walls 3.5 to 12 millimeters thick feed into an upsetting line. Induction coils heat only the end. A die then thickens the wall from the inside out, squeezing metal into itself. A second machine finishes with high-speed end forming, producing a 90-degree transition from full pipe to reduced end. Try shaping metal like that with a hammer and a very optimistic attitude. But raw shape is only half the job. The other half is trusting every one of them. Tubes drop in one end, a laser scans length, and anything wrong gets kicked out before it wastes a shift. A CNC arm carries the survivors to induction heating. Between shots, dies get sprayed with lubricant, miss that step, and the die welds itself to the part. Speed is not what limits production. Holding each part long enough to keep it from warping is. Rush that step and an entire batch can end up in the scrap bin. A rotor shaft is only as accurate as the machine finishing it, and those finishing machines have a spinning heart of their own, called the spindle. The spindle transfers every last newton of cutting force into the workpiece. A rough spindle produces rough parts, and no software patch will save it. So the good ones are built in climate-controlled rooms on a dedicated line covering 728 square meters. Put up in just 18 months for one reason. A temperature swing of even a degree changes dimensions the human eye cannot see. Blanks arrive from an automatic warehouse on driverless carts. Not every electric vehicle component fits on a shelf, though some of them are the size of a small car. Motor housings, drive unit bodies, gearbox casings weighing several tons each, still needing to be cut and bored to within a few microns. That happens on floor-type and bed-type milling machines, big enough to walk inside. Heads swap themselves. Probes align the workpiece automatically, before cutting even begins. Underneath the entire cutting assembly sits a system called Dynamic Active Stabilizer, which sounds like brochure noise until you learn what it actually does. It senses chatter, the low-frequency shake that ruins a surface finish, and cancels it faster than any human ear could catch. Without that system, you get a wavy bore, a wobbling rotor, and a warranty claim nobody wants to file. Why does it matter for an electric vehicle? Because that housing has to hold the rotor spinning at extreme RPM without letting it drift even a few hundredths of a millimeter off-center. The real cost is never the price tag, it is the total cost of ownership over the machine's lifetime. Buy the cheaper one, and you usually end up paying for it later. And those extra costs eventually find their way into the car, sitting in your driveway. Bigger parts mean bigger holes, and bigger holes mean bigger holes mean bigger machines to bore them. Multi-spindle heads swap heavy-duty cutters from carousels the size of a small warehouse. Deep bores drill straight through solid metal blocks while coolant floods the surface at pressure, flushing chips away before they can jam the cutter. Large components rotate on their own automated platforms, so the tool never has to reach around them. Get one bore wrong and the entire housing is scrap, but the network hiding between motor and wheels has not even started yet. Between the motor and the wheels sits a network almost nobody in the audience has ever thought about. Some of it is standard, pulled from catalog and shipped by the pallet. Some of it is standard, pulled from catalog and shipped by the pallet. Some of it is drawn from scratch for one specific vehicle, prototyped, tested, certified against standards outsiders never hear of, then pushed onto a production line that has never made that exact gear before. You will never know these parts exist. That is precisely why the car works. Once those parts exist, they still have to end up in the right order, in the right hands, at the right torque. A gear does not just spin, it converts speed into torque, and getting that conversion wrong ruins how the vehicle performs on the road. A three-stage gearbox does it through 3 gear sets, each one passing power to the next at precisely controlled spacing. Spread the parts across a workbench, and they seem ordinary enough. Assemble even one of them incorrectly, and the gearbox will never work as intended. Bearings first, then the third stage assembly, then the gears, which must face the correct side. Get that backward, and the gearbox will run for a while, then stop being a gearbox. Rings follow a specific sequence: thin ring first, thicker ring later, spaced by internal parts because the whole stack sets internal preload. Oil comes next, and the exact quantity depends on the mounting orientation, which is why every unit ships with a catalog most owners will never open. Every threaded surface gets anti-seize grease before assembly. Screws torqued in a circle warp the housing. Diagonal only. Amateurs learn this the hard way. Every one of those gearbox pieces was cut somewhere first, and cutting is where the precision actually gets locked in. A CNC mill drills a bolt pattern into a round housing blank, while coolant floods the surface and washes every chip clear before it can drag across the finish. A vertical machining center threads its way down a shaft, forming gear teeth as it goes. A friction saw throws so many sparks, the whole cabinet looks like it's on fire, and the operator behind the glass barely looks up. The cut runs clean, the disc separates, and the machine moves to the next blank. Elsewhere on the floor, a collaborative robot picks parts off a conveyor, flips them, and drops them into the next fixture with no human anywhere in the frame. Final check. A probe smaller than a pencil tip, sweeping the inside surfaces to catch geometric errors nobody could feel by hand. Drivetrain components don't all come from one shop. Gears, tensioners, couplings, reducers, each has its own specialist line tuned to one narrow problem. 70 years of quietly keeping other people's machinery from grinding to a halt in the middle of a shift. And before any of these parts ever meets an engine, they all pass under the same judge. An automated robot runs a three-dimensional laser scan across every surface of every finished component, catching geometric errors human hands could never feel. Only the parts that pass leave the facility. One checked gear at a time, an entire hidden network wakes up and gets on with turning the wheels. Before a car is a car, it is a puddle of glowing orange liquid. Wheel hubs, axles, differential parts, the load-bearing bones of the vehicle, all start out inside a furnace at temperatures that would melt most of what you own. An automotive foundry hitting 50,000 tons per year of production is not casually pouring metal into shapes. Every batch has to arrive at exactly the right chemistry. Silicon, manganese, carbon, a few tenths of a percent off, and the finished hub either cracks under load or wears out 3 years early. Cores get made in specialized machines running the cold box and shell core methods in sizes from 25 to 60 liters. That is what shapes the internal cavities of the casting before any liquid metal shows up. Get the core wrong and the finished part looks perfectly normal from the outside, right up until the moment it doesn't. Every finished casting gets checked chemically, physically, and by ultrasonic testing with reference samples filed away against EU standards. You do not send a hub out the gate without knowing exactly which melt it came from. Somewhere down the line, someone is going to ask. Pouring the metal is the visible part. Everything before and after it is where the real work sits. Engineers run flow simulations on CAD models to see how the liquid steel will actually travel through the mold, where it will cool first, where it might trap gas, where shrinkage will pull a void into the casting. Then a CNC machine carves foam patterns to match. Sand molds get assembled around them, coated with heat-resistant paint, dried with fire. The arc furnace melts scrap steel into glowing liquid, and a spectrometer takes a sample before the pour. Green light on the readout and the pour goes ahead. Red light and someone has to explain to the shift lead why the next 4 hours just evaporated. Once solidified, the raw casting gets scanned by 3D laser to check whether its geometry matches the drawing. Every difference against the CAD file shows up on screen before the part leaves the shakeout area. A foundry runs on rules that mostly come down to metallurgy and temperature. The plant here sits on a 10,000 square meter site with 3,500 square meters of enclosed workspace, plus another 2,000 square meters machining shop next door. The equipment list gets a bit unhinged if you are not in the business. A sandblasting machine rated at 1.5 tons per load. Induction furnaces at 500 kilograms, 3 tons and 5 tons of melting capacity. A sand reclamation system that prepares 40 kilograms of molding sand every 15 seconds. Why the range in furnace sizes? Because different products need different melt volumes, and firing up a 5-ton furnace to cast one small roller is a spectacular way to burn through the monthly power bill. The real constraint for most foundries is not skill, it is electricity, and everything else gets easier once that is under control. The output covers cast iron, cast steel, aluminum, ductile iron, manganese steel, and high chromium alloys. Every casting gets temperature monitored through thermocouples and chemically checked with spectral analysis, with heat treatment in a 20-ton furnace before it heads to machining. Scale up the operation and the number of checkpoints starts getting genuinely alarming. A steel casting facility running 4,000 tons of annual capacity on a 7,500 square meter closed area does not tolerate improvisation. The setup here: full automatic vertical molding size 4, automatic core shooters at 15 and 25 liters, induction furnaces at 500 kilograms and 1,000 kilograms and 1,000 kilograms. Every part gets shot blasted, heat treated, then hit with metallographic analysis, Sharpie impact testing, and ultrasonic inspection before it can move to the next stage. Casting the steel is only the opening move. Then comes the part where the raw shape gets pushed into something the driveline can actually use. After pouring and shakeout, the casting goes into a heat treatment furnace, then straight into a water bath. The thermal shock rearranges the internal grain structure and pushes hardness up dramatically. Grinding removes flash and excess material. CNC turning and boring finish the critical surfaces. Surface hardening applies a localized quench to the zones that will see the worst friction, sprocket teeth, roller contact bands. Then magnetic particle testing hunts for hairline cracks that would otherwise stay invisible until the part was already in service. A serious steel foundry gets measured in tonnage, decades, and a number of times the equipment has been rebuilt on-site. A furnace equipment has been rebuilt on-site. A furnace interior reaching 1,600 degrees Celsius. A 12-ton AOD converter for producing high-quality steel. Free forging capability up to 6.5 tons on a 1,000-ton press with a 6-ton manipulator. Nine heat treatment furnaces and 72-ton water and polymer quench pools handle parts up to 10 tons. Machining capacity finishes castings weighing up to 12 tons apiece. You do not casually machine a 12-ton part. It takes days, the cutting tools cost a fortune, and one bad clamp reading can write off the whole piece before lunch. The tricky bit with steel casting is that small errors do not stay small. Wrong pouring temperature, sulfur creeping above spec, moisture in the mold. Any of it produces internal defects that ultrasonic testing eventually finds after the machining is already done, which means the metal already ate a week of somebody's schedule before revealing it was scrap. Flexible production lets one facility handle both single-piece orders and 1,000-unit runs on the same equipment, retooled between jobs. That flexibility is why heavy-duty automotive castings still come from foundries like these, decade after decade. Aluminum casting for the auto industry runs on completely different physics from steel. Lower melting point, faster cooling, higher sensitivity to gas absorption. An aluminum melt will happily pull hydrogen out of the surrounding air and turn your finished part into a porous mess of tiny voids. That is why every batch gets grain refining, modification, and degassing treatments in fully automatic machines before it ever sees the mold. Chill mold casting, low-pressure die casting, gravity tilt pouring, sand casting, the method gets chosen to match the specific geometry and mechanical demands of the part. After casting, heat treatment tunes the alloy's physical properties. Then the lab work begins: chemical analysis, density testing, tensile testing, hardness, surface roughness, optical metallography. Every one of those tests exists because at some point in analography, every one of those tests exists because at some point in industry history, somebody skipped it and paid for it. The aluminum casting still has a long way to go before it meets its final dimensions. 5-axis vertical CNC centers work parts up to 2,500 millimeters long. 5-axis CNC lathes with simultaneous machining handle, rotational parts straight to customer drawings. Every stage gets checked on 3D coordinate measuring machines accurate to 2 microns. 2 microns off, and the assembly line sends the part back before it ever gets near a car. Every foundry faces the same 3 challenges: cheap imports, rising energy prices, and a shortage of workers who actually know how to run the equipment. One supported project cut scrap by 36%, enough for a foundry to finally hit its daily quota for an automotive customer. Scrap rate is the number that decides whether the month made money or not, and one bad shift is usually all it takes to lose it. When a part is too small or too detailed for sand casting, the process shifts to investment casting, a slower method built around wax patterns and ceramic shells. Investment casting starts by injecting molten wax into a metal mold to make an exact replica of the finished part in soft wax. Multiple wax replicas get assembled onto a central wax stem, a tree that will eventually feed molten metal to every casting on it at the same moment. The tree gets dipped into ceramic slurry, then coated with refractory sand, repeats several times, and the whole thing ends up wrapped in a hard ceramic shell. Then the tree goes into a steam autoclave. Heat melts the wax and drains it away, leaving hollow cavities in the exact shape of the parts. Sintering hardens the ceramic. Molten steel gets poured into the still hot shell. Once solid, the ceramic gets shattered off, revealing metal parts still attached to the tree, ready to be cut free. Then comes the finishing marathon: shot blasting, belt sanding, well repair, digital caliper measurements, liquid penetrant testing on every surface. 15 stages in strict order, and any one of them can quietly ruin the batch. Scale that same investment casting logic up to one of the largest operations in India, and the numbers stop looking cute. Full CAD to CAM engineering design at the front end. Automatic wax injection machines. Skilled workers assembling wax trees. Ceramic shell building through repeated slurry dipping and refractory sand coating. Then dewaxing in a pressurized autoclave removes every last trace of wax, leaving nothing but hollow ceramic. Induction furnaces melt the alloy at over 1,500 degrees Celsius before pouring into the preheated shells. Why preheat the shell? Because dumping 1,500 degrees Celsius metal into a cold ceramic mold shocks the ceramic and the whole tree ends up on the floor, along with the entire day's plan. Knockout breaks the ceramic. Cutting separates the castings from the tree stem. Machining and finishing shape the final surfaces. Then quality assurance coordinate measuring machines, spectrometers, and non-destructive testing. Customers span automotive, oil and gas, valves, pumps, and aerospace. In industries like these, a defective part does not just cause a return, it can cause a shutdown that costs a customer more per hour than the entire order was worth. Here, Kurtzon is showing the finishing stage of a cast metal housing. The rough body has already been formed, then clamped inside a machining station. Cutting tools refine the circular opening, smooth the sealing face, and bring the inner bore to its final shape. Around the outside, the ribs, lugs, and bolt areas remain visible from the casting. After machining, the part leaves with a clean metal edge, accurate contact surfaces, and a ready housing for the next assembly step inside the line. A cast housing is checked after machining. A measuring probe touches the flange and bore area, confirming clean edges, bolt holes, and contact surfaces before the part moves to another stage. Watch the same production line at scale and one detail stands out. Nothing here happens once. Molten metal pours into rows of molds on a conveyor that never stops. Samples go straight from the pouring station to a lab where composition gets verified against the exact recipe on file. Approved cast metal housings move to CNC lathes for turning, then to grinding for surface finish, then to coating booths, then to laser marking, then to controlled assembly under measured hydraulic pressure. The lab is where the batch actually gets its verdict. A spectrometer analyzes the poured sample, confirms carbon and silicon content, and either releases the melt for casting or sends it back for adjustment. No exceptions, no exceptions. Down the line, a robotic gripper picks finished products off the conveyor. A laser burns the serial code into the metal, and the part becomes traceable back to the exact melt it was cast from. The final check happens by hand. A dial indicator sits on the finished product, and operator turns the part slowly, and any runout beyond spec kicks the piece off the line, no matter how far it has already traveled. In a modern gear factory, parts do not sit around waiting for a human to notice them. They move. The moment a gear finishes on one machine, it joins a tightly organized flow instead of waiting on a shelf. This factory covers 115,000 square meters, employs more than 400 people, and produces thousands of different gear components. Every year, hundreds of new products get added while finished parts shipped to customers in more than 78 countries. That level of production creates a problem no person can solve alone. The warehouse contains over 18,000 storage locations, and every gear has to be picked, tracked, and delivered at exactly the right time. Finding the right part by memory is impossible, especially when many gears look almost identical. What is the math force automation? A single truck gearbox contains many different gears, each made to a specific size and ratio. Multiply those parts across different truck models and export markets, and the number of unique components climbs into the thousands. Automated storage and transport systems keep every part moving to the right place without delays or confusion. Workers supervise the process, while machines handle the repetitive lifting. and production stays accurate and steady from one order to the next. The trick with automated machining is not the cutting, it is the moving. A twin-spindle vertical pickup lathe grabs the raw part from a tray, machines it in two synchronized workspaces, and drops the finished piece back in, all inside a footprint of just 9.6 square meters. You could fit the whole machine in a suburban garage. Scale up the same idea, and the parts get bigger without slowing anything down. This vertical pickup CNC lathe machines chuck parts up to 300 millimeters across and loads them automatically. The vertical design lets chips fall away by gravity, which keeps the cutting zone clear without anyone reaching in with a brush. Push the diameter to 400 millimeters, and the machine is now handling full turret discs while still loading itself. Bigger parts do not need extra handling. Automatic loading, multiple cutting tools, and continuous machining keep production moving while the operator gets on with other work instead of babysitting every cycle. And when the parts stop being cut and start being joined, the humans still stay out of it. A differential housing arrives at the loading conveyor. A camera detects its exact orientation. A laser cleaning station scans around the gear ring, burning away oil and contamination in seconds. No chemicals, no wipe down. The workpiece then gets assembled, measured, and laser welded, all in one clamping. A live monitor watches the weld's power, temperature, and plasma signature, flagging defects in real time. Ultrasonic testing checks the finished joint. The whole cell needs one operator whose main job is making sure the machine still has parts to work on. Almost nobody looks at a wheel and sees an engineering problem. But that is exactly what it is. A wheel has to carry weight, absorb impact, hold its shape under braking heat, spread load into the tire evenly, and spin true at highway speed, all while looking good enough to justify the sticker price. The process starts inside CAD software. Where engineers sketch structure and style. Advanced simulations then test material stress and model how liquid aluminum alloy will actually flow into the mold during casting, because a wheel with even one small internal void turns into a safety recall waiting to happen. Aluminum alloy melts in industrial furnaces at tightly controlled temperature. Low-pressure die casting pushes the metal into shape. Then heat treatment optimizes the grain structure and raises hardness. That is the step that makes the wheel actually strong instead of just wheel-shaped. CNC turning and milling refine every surface, drill the lug holes, and cut the fine details. Then, X-ray inspection scans every wheel for internal bubbles or hairline cracks that no outside look could ever catch. A wheel that fails on the highway does not just ruin one driver's afternoon. It follows the manufacturer around for years afterward. Before wheels and before any large cast automotive part get anywhere near a machining line, they need to lose the sand. Fresh castings come out covered in molding sand that has to be stripped off entirely. A shot blasting cabinet does that at industrial scale, parts up to 3,200 millimeters wide and 1,000 millimeters tall, weighing up to 25 tons each, ride through on a roller conveyor at 0.4 to 2.0 meters per minute. 4 high-performance turbines above, 8 below, angled to hit every surface in a single pass. Miss even one hidden pocket of sand and the follow-on machining turns into an expensive fight with the cutting tool. A wheel is nothing without what spins inside it. Rolling bearings turn friction from a destructive force into a controlled one, and the operation making them runs on a 50-hectare science and technology park dedicated to that one problem. The setup is unusually vertical. In-house R&D, in-house material inspection, laboratories, one of very few bearing makers on Earth that actually test their own steel instead of trusting whatever certificate the supplier hands over. Every batch of steel gets analyzed on arrival. Every product batch gets checked throughout production, and again at final inspection. About 70% of output ships to international markets across 5 continents, headed straight to OEM assembly lines under just-in-time schedules. Why the paranoia about steel quality? Because a wheel bearing failing at 120 kilometers per hour is the sort of headline manufacturers spend the next decade trying to forget. And here is the last twist, the one the audience never sees coming. A car is not built by a car company, not even close. Behind every finished vehicle sits a network of thousands of specialist suppliers, most of whom will never appear in a single advertisement. Foundries pouring the hubs, heat treatment plants hardening the gears, bolt factories running 24-hour shifts, bearing makers checking their own steel, gearbox assembly lines, aluminum wheel plants, machining specialists, rubber and hose producers, fitting and adapter suppliers. Consider just one slice of that invisible layer, the hydraulic side. Every truck, every construction vehicle, every piece of heavy machinery depends on hoses and fittings that carry pressures the average driver would rather not think about. 6,500 psi in a hose is not unusual, and that number gets less comfortable the longer you sit with it. An industrial supplier operating on that scale is not just cutting rubber. It runs certified production of high-pressure reinforced hoses, forged fittings, precision adapters, all made across facilities in multiple countries, all designed to survive years of vibration, temperature swings, and pressure spikes. Vehicles for construction, wind power, hydrojetting, mining, drilling, cranes, agriculture, marine, offshore, every one of them needs hydraulic circuits that will not fail. The certifications tell you the seriousness, ISO PED, industry-specific approvals. Behind those certifications sits a testing laboratory the size of a warehouse. When your product connects a 200-ton excavator to its cutting arm, close enough is not a phrase anyone in the building is allowed to say out loud. Zoom in on one plant, and the paranoia gets very specific. Every hose gets cut, crimped, and pressure tested. One system tests each finished assembly against its rated working pressure in a sealed booth before the packaging tape even comes out. Either the readout says conforming, or the batch goes back and nobody looks happy about the second option. The material science underneath is where most people would tune out. So here is the short version. Rubber compounds get developed in-house by an R&D unit that then blends them on modern mixers with electronic control of every input variable. 2 hose technologies. Flexible mandrel up to 1-inch diameter rigid mandrel for larger diameters. Braiding and spiraling systems, layer and steel reinforcement. For fittings, CNC and transfer machines have replaced older cutting oil setups, allowing lead-free and forged raw materials, cutting steel consumption. When your customer base is basically the entire global commercial vehicle industry, "We've always done it this way," tends to stop being an argument that wins meetings. Two plants, two very different rhythms of work. One extrudes hydraulic hose from raw polymer, braids steel reinforcement into it at high speed, measures the diameter with laser scanners accurate to hundredths of a millimeter, and coils finished hose onto reels the size of tractor tires. The other machine's fittings on CNC lathes, then feeds the finished parts through optical measurement stations and infrared vision systems that check thread geometry automatically. 2 factories, 1 quality system, millions of parts leaving each month at the same tolerance. And then there is the logistics part that nobody thinks about until it goes wrong. Custom hose assemblies configured on request, pressure tested on-site, then dispatched with 48-hour delivery across an entire country. When a construction site sits waiting for a hydraulic line, every hour of downtime costs somebody real money. When a hose fails in the field, the fix has to arrive fast, sometimes right at the customer's site. Portable hydraulic hose crimping machines take the same industrial-grade dies from the factory and shrink them into something a technician can actually carry. Hand pump versions, foot pedal versions, modular versions where the crimp head separates from the power pack. The dies do not care how small the machine is. They care about the crimp pressure, and they hit it. And behind every one of these mechanical networks sit the sustainability numbers. A new solar installation projected to generate over 300,000 kilowatt-hours every year. A packaging switch from plastic to recycled paper and wood, cutting plastic use by 70% across the entire product line. Around 300 people spread across 5 sites, split between production and commercial logistics. 4 divisions serving industrial, food, motorcycle, and OEM markets at the same time. The invisible suppliers are quietly cleaning up their own environmental math, while the car brands take the photo op. Then there is the pure specialist, the one doing exactly one thing for the entire industry: precision mechanics since 1974. Cutting, centering, facing, turning, milling, rolling, assembly, and balancing, mostly on shafts and flanges destined for high-technology drivetrains. 133,000 square meters of industrial surface. ISO 9001 certified since 1998. Exports across Europe, North and South America, and beyond. Spend 50 years focused on one craft, and it stops feeling like just a business. It becomes the reason the business exists. It becomes the reason the business exists. Even the parts of the car you actually look at have their own hidden network. Emblems, monograms, interior and exterior moldings, the visible decoration get produced in 8 branding plants across 4 countries: Spain, Portugal, USA, Mexico, generating 163 million euros of turnover by 2025. The processes stack up in ways almost nobody would guess. Plastic injection molding, galvanizing, painting, screen printing, die cutting and stamping, pad printing, die cutting and stamping, pad printing, screen printing, die cutting, enameling, membrane switch manufacturing, adhesive die cutting, metal embossing and brushing, flex chrome and IMF technologies, PVD coating. 12 different technical processes go into making sure the badge on the hood looks right. And then there are the specialists whose entire existence revolves around one narrow category of parts. A gear producer founded in 1987 with a single lathe in a 50-square-meter workshop. Today, it manufactures gears and gearboxes for Volvo, Scania, Mercedes, Iveco, MAN, and DAF trucks, 6 of the biggest names in commercial vehicles on the planet. The path forward was deliberate, in-house heat treatment and case hardening plants built in 2003, backed by ISO 9001 certification, a switch from universal to CNC gear machines to hit European tolerances, a hot forging plant added in 2010. Today, the operation covers 30,000 square meters, employs 200-plus people, exports to 50 countries across 7 continents, all from a garage-sized shop that started with one machine and a lot of stubbornness. Some specialist suppliers reach numbers that stop making sense on paper. One bolt and brake component maker exports to 117 countries. Molten metal at one end of the plant, finished, laser-marked, precision-inspected products at the other. And the pattern always looks the same when the camera walks the floor. Electromagnet loading scrap, slag skimming, molten pores transferred by forklift, automatic mold lines, central control rooms, grinders throwing arcs of sparks across the paint booth. Different plant, same choreography, everywhere in the world. CNC lathes running heavy-duty programs, presses stamping bolt heads, thread rolling machines, and dimensional inspection by digital caliper on every batch. The paperwork alone would fill a filing cabinet a week. And then there is the industry within the industry. Heat treatment. A specialist plant does nothing but harden other people's parts. Loads arrive as raw castings and forgings. They come out with the exact hardness profile that lets a shaft survive fatigue cycles or a gear tooth resist wear. Induction hardening with continuous water quench. Vacuum furnaces to prevent surface oxidation. Optical microscopes at Leica-grade magnification to verify grain structure. Digital hardness testers on every batch. The plant does not make anything of its own. It just makes everything else last longer. And every car on the road depends on shops like this. Another heat treatment specialist. 2 facilities, different heat treatment processes, Give steel the exact hardness, strength, or toughness each part needs. Small components travel through automated conveyor furnaces without being touched by hand, while larger parts follow carefully controlled heating and cooling cycles. Every batch stays monitored to keep the result the same from start to finish. Because in these industries, unexpected downtime tends to cost customers considerably more than the parts themselves. And underneath all of it sits the unglamorous reality most drivers never think about. Milling and boring are the two operations that produce a shaft hole with the right position accuracy and internal geometry. Milling removes material with multi-point rotary cutters. Boring enlarges an existing hole with a single-point cutter, tuning its diameter to fractions of a millimeter. Both happen on a CNC gantry boring and milling machine, heavy-duty equipment designed for large parts, where position accuracy matters more than raw cutting speed. Every valve, every hydraulic body, every drivetrain housing on your vehicle went through one of these at some point. Behind every one of these plants are the people you never see, the shift workers, the inspectors, the packers, the drivers. So here is what you actually own when you buy a car. You own the finished product of thousands of factories most people will never hear about. Foundries, forging shops, heat treatment plants, bearing makers, gear specialists, bolt manufacturers, and countless other suppliers all contribute to a single vehicle. Every one of them has spent years perfecting parts most drivers will never notice. Look at the car sitting in your driveway right now. Which invisible part behind it do you think matters most? The bearing, the bolt, the forged gear, or something even smaller that almost nobody ever notices? Drop your answer in the comments, and if this changed the way you look at your car, share it with someone who still thinks a car gets built by the car company. Thanks for watching. The invisible world keeps building. Subscribe. The next one is even wilder.